Hi everyone. Today's talk is Can you trust your AI? That's the title. I don't want to start saying that AI is bad. So I'm going to guide through, let's say, this type of journey, starting from, starting from a pitch. Voxed Day Milano is going to happen is in September. We have the call for paper that is open. You can buy ticket. So the call for paper is going to finish in next Monday. So feel free to drop a proposal or more, or buy some ticket, or ask me if you have any question, or you can reach also Mario around the venue. So artificial intelligence. Let's start with some definition, because it's a very large topic, and in reality there is no real single way to define it. So I sort of like this Wikipedia definition about that artificial intelligence is intelligence demonstrated by machine. So it's a very general definition. So traditionally they are divided in symbolic AI, so rule, logic-based, and sub-symbolic AI, statistical learning. They are different way to approach the problem that you still wanted to try to automate task, so use a machine instead of a human. So let's start with prologue, symbolic AI. You have a very simple way to express knowledge. So if you know relations, if you realize how to describe it, it's quite powerful just to tell the computer, okay, I know what sibling means. It means that they have the same parent. And I also have the possibility to define what parent-child means, so the relationship about parent-child. So I can insert some fact, so some information that I know, and I can ask the system to use the rule, so the predictive that they know, to infer new knowledge. It's a very powerful way, and it's a very, let's say, natural way to express knowledge that you can easily express with relations. The rules, it's a rule engine that can be used for a similar scenario. You can specify a rule, so you can specify that when a specific condition means that I want to insert new fact, so I'm able to, given some data, I'm able to generate new data, so generate new knowledge. Then I insert some of them, and then I can query the system, say, okay, can you tell me if this is happening? And even here, it's another simple way to describe your symbolic AI. There are higher level abstraction in the same field, so I can use a decision table. In the decision table, it's mainly a way to express what you can write with rules in a way that it's a bit higher level, so you can focus about maybe the different value that you want to express, but still, it's a way to express the knowledge that you want, and then you can ask the system to use this knowledge to infer new intelligence, new result. Of course, this doesn't cover all the possible use cases. There are use cases where, like image recognition, anomaly detection, where in general symbolic AI, it's not really easy to apply because it's very hard to express with predicates, like the definition of what is in image recognition, what is a cat. Because I mean, you can realize, so you know how to realize it, but it's very hard to express with rules. So let's move to ML. So in machine learning, in reality, it's a very wide topic. So there are many different types of algorithms that are part of the machine learning, let's say, ecosystem. Clustering, if you wanted to classify data, neural networks, for example, for image recognition, linear regression. So there are many techniques that you need to know, you need to learn, and especially you need to understand when to apply. One of the key features compared to the symbolic AI is the fact that they are able to learn from data. So usually you are able, as human, to say that all those pictures are from cats. So you can express, you can label your data, and now you just need that the algorithm automatically is able to infer that what was the relationship between them. And this can be used, for example, for also similarity in terms of customer similarity, and this can be used for a recommender, because if the algorithm is able to realize that these two customers are behaving in the same way, and one customer has 5 products, the other one has 4 products, I can propose to this customer the additional product to see if he's interested in. One other nice characteristic is the possibility to handle noisy data. So in general, it's possible if you have, if you have IoT, if you have many data that contain some noise, because they are not, let's say, a perfect value. In symbolic AI, if you just have, I don't know, age as value, and this value is wrong, this will be used to infer some logic, and it's just wrong. So random forest, linear regression, and similar are all ways to be able to provide a result, a good result, even if there are some noise in the data. So in a nutshell, the idea is there is no one, I mean, it should not be used one or the other, they should be used together, because if you know what you wanted to express, so if you have some decision that you want to apply to your system, like I want to provide this specific, I don't know, discount calculus because that's the way that I wanted to apply, I should be able to express using digital decisioning, symbolic AI, while if I have a relationship that needed to be extracted from the data, so I'm not really able to express them in a simple way, I can use machine learning. On top of this, you can also use mathematical optimization, that it's a sort of different additional approach when you have a planning problem. So for example, let's assume that you are in e-commerce. You are using machine learning to realize that you wanted to suggest a specific product to a customer. You wanted to do some reordering with digital decisioning, like even if this is the suggestion, I wanted to clean up product that this customer already got, similar to the example that early today Mario explained. While with mathematical optimization, for example, as soon as the deal is closed, so now I needed to ship my package, I would like to optimize my let's say all my chain to be able to match, for example, market need, like I wanted to ship the product in 24 hours, but without, of course, dedicate a track per package. So you wanted to optimize that part. That's all. Well, not really, of course, because otherwise the talk was like 5 minutes. As soon as you take AI and you put in production, something can go very wrong. And sometimes the output could be, let's say, quite, funny. So in this case, there was an AI-trained camera that was trying to replace the human, because the main idea was, okay, if I'm able to follow the ball in a football game, I should be able to follow the action. Well, unfortunately, this model has not been trained considering the fact that the referee can be bold, and it was just making a wrong assumption about the fact that the head of the referee was the ball, and the final effect was that people from home was not really able to follow the game. In this case, I mean, it was a quite funny outcome, but what if I submit my resume to like a company, and there is a pre-processing that try to do screen scraping and that try to do scraping to automatically classify my CV. And after they realize that this model actually has a bias against women, so if you are a woman and you are applying to that position, you are more unlikely essentially it's quite unlikely to happen that you are going to be called for that position. Well, in that case, the outcome is very, I will say, not fun at all. This is a very recent additional scenario. It's a very powerful AI system that, given a text description, it generates an image that try to describe, that try to represent what you are expressing. And they realize that if you're using a gender-neutral term like nurse, like CEO, in reality, he's making an assumption like if you're looking for a nurse, it generates all-female picture, while if you're looking for a CEO, it's generating only picture of a male. And even in this case, of course, it was not really something that people that trained this model was expecting. And of course, in this case, you can be sued for gender bias, and in general, if you're applying this system in production, this can, let's say, produce very bad outcome for a reputational, but not only. Because even if you are not still convinced about, okay, this is what I need, this is, let's say, a problem that I have, there are some regulators that are saying that, like GDPR, but there are other, like in California, in UK, I think, that are trying to follow the same approach. Your customer has a sort of right of an explanation. So even if you are using artificial intelligence to make a decision, this doesn't prevent an end user to say, okay, tell me why. So why you are, let's say, tell me that I'm not able to get my loan, why I'm not able to get the output that I want. And you should be able to provide meaningful information about the logic involved. Of course, it's a quite general term, because of course they cannot really go deep and say you cannot use a neural network for this type of use case. So they try to define the principle, they try to define the context and the boundaries that you needed to apply to, if you wanted to use, say, artificial intelligence in production with an effect on an external customer. So, for example, a user can say, okay, tell me why, give me the information, give me visibility about what's going on. So, in Red Hat, and the team I'm working with, that essentially it's rules, we started to think about, okay, so what are the characteristics, what are the aspects that we would like to achieve to be sure that our model, AI, generic AI service, is able to, let's say, we are confident to use it in production. So one aspect could be about monitorable, because again, even if I trained my model with perfect data, people behavior change. So my model was perfect at the time of deploy, but after 6 months, for whatever reason, now the model is not really able to let's say, handle the data, the real data that are coming. So I needed to continuously monitor the system and making sure that it's still behaving as expected. On the other side, auditable, because again, if I made a decision and someone is going to challenge me, say like, okay, tell me why, especially if I think about a scenario where I have a continuous learning. So my algorithm is changing continuously. This is a very tricky scenario because essentially every time it's a sort of unreproducible scenario. I got my input, I produce the output, and in reality, if I wanted to replicate the scenario, I should be able to take a snapshot and say, okay, this was exactly the version of the model used at the time, those was the actual input used at the time, so that I can essentially replicate if I want. And then the explainable one, because again, we are in a scenario where ML could be very cool, a very nice technology to use, but I should be able to explain for myself, for internal purpose, and for external purpose, what is going on. So let's focus a bit more, because I think that for a monitor perspective, an audit perspective, it's okay. You can realize that you need it, but it's probably reasonably clear what you can put in place. While for explainable, it's a quite, I will say, it's a more tough problem, and that requires some additional, let's say, investigation. We are not, of course, the only one that was thinking about something like that. One of the first that produced a presentation about what is being called explainable AI, it's DARPA, and they was trying to have a very high-level definition about what they were aiming for an AI system that provide, let's say, that is explainable, that provide trust. So if you think about the first, let's say, path about what we have today, so today we have images, we have learning, and we have a final result that it's a very, let's say, obscure for a person. It's like, okay, I'm sure this is the output of this model is that given a specific input is that this is a cat with a level of confidence about 0.93. Okay, I can trust the system, I cannot trust the system, but essentially I don't have many additional information that give me the possibility to better understand why the model is providing a similar result. So what I would like to have from a theoretical perspective is essentially a sort of explainable interface that give me not only the output and the level of confidence, but also like, okay, it's a cat because I was able to recognize the shape of the hair, I was able to recognize the color, I was able to recognize the fur. So I provide some sort of characteristic about what I used to take my decision. Of course, this was just a sort of ambition. It's like where we are and where we would like to be. They also did some additional analysis about, okay, given that AI it's a very large topic, there are a lot of different techniques, and they try to do the sort of classification, because a key aspect when you wanted to use AI in production is to even spend time about thinking about which type of model you want to use. Because some techniques are less explainable, and they are intrinsically less explainable comparing to other. So you should be able to think about what is an algorithm that fits your requirement, but is, let's say, already a good starting point from an explainability perspective. So the whole explainable AI, let's say, stream aim to improve the explainability for each model, for a neural network, from a decision table, for whatever type of algorithm that I want to use. At the same time, it's, let's say, very unlikely possible to really make all the possible algorithms explainable with the same level of understanding from a human being. So another aspect is about which type of explanation you wanted to provide. So you also need to think about who is the target audience for this information. So could be sort of business analyst or someone that is providing the requirement. They usually know very well the domain, but they usually are not mathematician. So usually, if they provide them just KPI or plotting of the distribution of the data, they are not really able to understand if, okay, this is the level of quality that I was expecting. While for a data scientist, of course, it's the opposite. For a data scientist, you can provide many information, even low level, because they should be able to understand them. So let's start to classify a bit more what explainability, let's say, different type of explanation. It's a quite recent topic, so it's still ongoing at a research level. So you can find many different ways to classify them. You can find many different information. So let's try to introduce some concept. For example, local explanation versus global explanation. Local explanation aims to explain a specific decision, a specific result, while global explanation is trying to provide an information about how the model behaves in general. They cover different needs, and both are useful. On one side, what you usually want to have, it's a general understanding about how your model behaves before maybe using it. At the same time, each model has a sort of, let's say, level area that is not properly covered. So even if from a global perspective the model is perfect, you always want also to have a local explanation for the specific use case that the customer is asking. Because in the worst case scenario, it's an outlier. So the model has not been trained for that. So you are even if the model is perfect, you are getting better results just because the model has not been trained for that type of data. Interpretable versus post-hoc. So there are models that people are used, let's say, to understand, while in other you need to apply some additional algorithm or analysis to provide an explanation. Sometimes you are able to take a model that is quite obscure and you try to have a surrogate model. So a model that has the same level, let's say, of that approximated the first model, but with much better interpretability and explainability. Static versus interactive, because it could be just a, let's say, static value compared to an interactive tool that you can like question and say, okay, give me the information. Based on that, you can ask another one until you reach the level of explanation understanding that you have. Let's start with a couple of examples about explainable algorithm. So LIME, local interpretable model agnostic explanation. It's a local explainer, salience method. So it aims to provide, let's say, a classification for the input, for the feature, in your specific case, so in a local scenario, to understand for that decision who had the most positive and negative impact for that decision. So if I am applying for a loan and I got it refused, this type of technique should be able to give you like the information like, okay, the most important feature for that decision was your salary. So that's definitely the most important information that we use to take this decision. Let's see for this algorithm how it works, because it's a quite interesting approach for explain the model. So this is just an example about the distribution about, let's assume that this model is only answering yes or no, so true, false. It's like a classifier, and the two different colors are describing the different area. One, the area where I obtain true as a result, and the area where I obtain false as a result. This is my local explanation. So this is my input. So I got this result, and if I try, one thing that I can try is try to, okay, let's consider, let's say, take one of the features in the same value and try to analyze the rest of the space with the other feature. So I can try to sample more or less where I am. Another possible thing that I can do is try to move, let's say, test a lot of different values to try to understand the shape of my model. The assumption that LIME, or let's say the consideration that LIME is making, is that if you focus on your local data, so if you don't really look at the whole model, but you look at only a specific space that is close to your model, you are usually able to approximate that with essentially a linear model. So if you look at that specific area, you see that it doesn't really care about that the shape of the result. It's very different. Near my data, you have the possibility to get clearly a separation. So why don't I just sample with additional inputs that are closer to the input that the user provided to understand where let's say, those values are, train a linear model, and extract the weight for each of the feature. And you know what? Those weights are the feature importance. So I'm making the assumption that I'm able to approximate my model locally, and given that, I can make this kind of calculus. This is just one of the example, of course, of the explainable techniques that you can use, but I'm trying to give you, let's say, idea and keywords about this type of field, so that if you are interested, you can go deeper and even try to contribute with new algorithm and research. Another type of explanation that it's very, from a point of view, nice for people that are not very, let's say, knowledgeable in terms of mathematical knowledge and data scientists, is a counterfactual explanation. So in most of the case, when you wanted to get an explanation, you are mainly hoping to get an explanation for, usually you get the result that you don't want, but you know the result that you were expecting. So like, okay, I applied for my loan, the loan has been rejected, so I was expecting to get it approved. So why cannot ask the system, okay, try to change my data to provide an additional input, an alternative input that was able to give me the result that I want. And in this case, the problem is that to minimize the shift, so that I wanted to stay close to my data, like, okay, if I have a system that say, if you can provide, instead of your salary, 10 times more of your salary, the loan will be approved, okay, thanks for the information, but I wanted to stay close to my data because it's very unlikely that I can really change dramatically them. And at the same time, of course, minimize the target cost. So minimize the, if possible, exactly get the result that I was hoping for. In a picture, it's probably way easier. So this is, let's say, the diagram with the space of, let's say, the distribution of let's say, the result. And age, it's my current value. And as you see, there are multiple values that can lead to a positive outcome. One is very close to mine. The other one is very far. So I wanted to the closest result as possible. And sometime even more, if I have, let's say, many features, I would like to, let's say, freeze some of them. Like, again, I might be able to change my salary, maybe not dramatically, but I'm able to provide more information, while I'm not able to change the number of children. Like, yes, I mean, there are ways that are not legal to change the number of children, but in general, this is a value that you don't want it to modify. So you should be able in a similar system to say, okay, those are the data that you want to change. Those are the data that I cannot change or I don't want to change. Try to make the algorithm provide me an input that match my expectation. The last one, and for this one, I'm not going to very deep details. It's about SHAP. It's a salience method, another method that aim to weight and let's say the different feature that you have, and try to calculate the contribution for each. It uses essentially different techniques, very different, based on SHAP values, to give you the information about, again, given a set of input that I use in my model, which of them has been used and added the most positive, let's say, added the majority of the contribution to my result. One interesting aspect, and this is true also for Lime, is the fact that starting from a local explainer, some usually are able to also tame a global explainer, just doing essentially an aggregation. So given that, of course, you are able to take a sample very close to my data, you should be able to test the whole space of my solution and then aggregate them to have, I will say, a general distribution, a sort of average distribution of the impact of my feature. So many techniques that move from local to global are essentially derived algorithm based on the first one. This is intended to be, let's say, an introduction, and let's say, I hope that I'm giving you a pointer in terms of what you can use and what you should pay attention if you really wanted to use AI in production, not only just for an experiment, but really have your business logic automated using AI. But there are many other aspects like fairness. And this is about, for example, when you change the model, you want to make sure that your model it still doesn't, I don't know, discriminate people or geographical bias. You would like to do a very I would say, strong analysis in terms of interpretability and simplicity analysis, so that you choose the model that very likely it's already interpretable. So that, for example, a decision table. In a decision table, it's quite understandable for a user what the model is doing. So I see that I have my tree, sorry, decision tree, not the decision table. I see my tree, and I see that at every level, I'm making a decision based on a specific threshold. Like, okay, based on age, I'm going to split. So I'm usually able to understand why the model is providing that specific result. So essentially, we are saying that probably what I would like to achieve all those three, let's say, characteristics before I can really have trust, let's say, in my system before putting in production. So what we did, let's say, was it's starting a sort of a new initiative named TrustyAI that aims to try to cover those aspects. So try to provide monitoring for your system, tracing, and accountability, so collecting information so that you can get more understanding about what you are doing and replicate it, and the explainable service, using the algorithm that I explained and many more. To do that, we are part of a family, so we are part of Cogito, mainly, that it's an evolution, mainly of rules and JBPM, that, sorry, that aims to, let's say, automate decision and processes in the cloud. And of course, we are using many other cloud-native technology, Quarkus, Kubernetes, operator framework, Knative. So the idea is usually you want, even if you are moving to a different stack, so the whole idea behind Cogito is that even if you're moving to cloud, the type of problem that you would like to solve are similar. So let's try to apply the same techniques that I got, for example, with rules in a different, let's say, ecosystem. And in this type of ecosystem, it's also where TrustyAI wanted to bring the additional information, the additional value. So Cogito, essentially, it's a microservice architecture. So we have you specify your ML, you specify your rules, you specify your process, you specify all the logic that you wanted to apply, and there is an actual runtime that runs it in a container, in JVM or native mode. And there are many other microservices that we provide, for example, to collect metrics, or for example, to interact with other services using message passing, or storing, for example, data for a query. So we have a data indexer service where data are stored and where a user can do the query. And Trusty, it's part of this ecosystem. So we provide an explainable service that is a microservice that is able to do this kind of analysis, and you can use it as standalone, or you can use together with the other services. For the monitoring, I don't know if you're familiar with Prometheus Grafana, but if you wanted to create a microservice, usually you wanted to also publish metrics. So usually you programmatically, using some tool, you generate those metrics. TrustyAI is able to introspect your model and generate some of those metrics for you, so that you can have a Grafana dashboard where you can, for example, compare the current rate that you have for, I don't know, positive approval of a loan compared to the negative approval of the negative result of the loan. And you can use that, and then on top of it, of course, you can implement some analysis or even alerting, like if I expect to have at least, I don't know, 5 requests per second and I see a drop, 5 requests approved per second and I see a drop, I can implement some alerting. So this can help you to build a proper monitoring stack on top of it. So the first part for monitoring is to extract metrics, so that at least you have the building block for build the whole additional, let's say, monitoring platform. Data are for tracing and for audit are saved and are showed using a UI, so that you can interact and you can go back in history and say, okay, let me see the decision that has been made like 2 weeks ago. Let's see not only the final outcome, like approved or rejected, but also see the level of confidence. And for each of them, give me some explanation. And this tool was aiming to target a more like a type of business analyst, so that we are trying to provide an information that it's consumable by them. So we are providing, in this case, for example, a feature scorecard chart. So we can see for each input that the user provided, what are the positive outcome and what are the negative impact. TrustyAI explainable library, it's at the end of the day a Java library that you can reuse. It covers part of those algorithms that I described, like LIME, partial dependency to plot, SHAP, controfactual, some aggregated matrix, generate some matrix that you can use. It also has a Python binding, so that if you're more, let's say, familiar with Python for your data scientist exercise, you can use a Python notebook, install using, let's say, the traditional Python stack, this library, and invoking it and use it directly in your system. It has also some integration with some open standard like DMN and PML that I'm not really introducing in this presentation. 10 minutes. Okay. Finally, some references. So you have a landing page that you can reach if you wanted to have more information about what you need to do. So we wanted to get more information about what you need to do if you wanted to start to use TrustyAI. There is a Python binding website where you can get those information. You can run a demo. You can access the explainable library and get more information. There are also, as I told you, it's a quite open research stream. So we also have a paper in preprint that aims to describe the techniques and compare to existing implementation that we hope soon will be published, but it's already available as preprint. And Red Hat, it's an open source company, so we have an upstream chat based on Zulip chat system where you can reach us and make questions and try to ask if you want to try or provide feedback. I think that, yes, that's the last one. I think that we have still some time for Q&A. Okay.
Yes, thank you very much for the talk. So I have a question about decision taking based on machine learning. If you want to approve somebody for a loan, for instance, would somebody wants to have a logical explanation why he got the loan or not? And will you ever get a clear logic explanation using machine learning? Or will it more be like, well, you scored like this on certain variables? So I'm wondering, how do you see that?
Let's say, in my experience, as usual, we also like to try new technology. So sometimes we are applying new technology for a problem that maybe doesn't really require to have that type of analysis, because you are usually able to express the type of information with a more traditional symbolic AI system. So we have customers that are trying to do similar analysis. There are also quite different approaches. For example, there are, I'm not covering it in this presentation, but there are techniques to use first an ML model to discover some relation and then generate a rule. So generate a set of rules based on the relation. So try to describe with an actual rule this relationship, so that there might be also some additional post analysis, like, okay, the model defined me a sort of baseline rule base generated automatically out of the data, and then I can tune, because I know that I don't want to use that value, or I realize that this relation that is in the data are not really meaningful for the model.
Would you then, for instance, say we use a machine learning model to determine who gets the loan, who not? So the people who get the loan, yeah, well, that's fine. Probably people won't complain that they will get the loan because they applied for it, and people who didn't get the loan, that ideally you would do some post-processing and maybe figure out should those people indeed not get a loan, and find out why exactly, what's the exact logic to not give them the loan, to decline them the loan.
Yeah, in that case, for example, for the loan use case, for example, that is one of the one that I saw in with some customer. Usually they mix and use ML mainly to define the threshold. So they don't want to provide upfront, like I know, for example, I know the logic involved to make the decision. So I don't want to also hide all the process behind an ML algorithm. While I'm not very sure if, let's say, the best risk score it's like a 5 or 5.2. Because this is based on historical data. I can learn, given like the past 20 years of loan approved, I can get like, okay, what was the most, let's say, what is the best threshold to minimize the possibility that the loan will be not paid back by the person. So you are essentially mixing the two approaches. So you're using ML only to identify a specific value that it's very hard to compute manually, because yes, you can try to guess it, but I mean, it's probably more effective to do if you do it, let's say, in a sort of expert system approach with a domain expert that does the value. Usually it's like a fixed value, like it's 5.24, because human beings usually are not really intended to provide a very floating point type of analysis. So that's the basic. And then on top of it, yes, you usually apply explainability, because in any case, you would like to have, for example, a very good analysis about, it could be about gender. So you should not really expect to have a loan approved based on gender, because it's very likely that you are discriminating people, or even geographical information. So you can use this as additional checkpoint, quality gate, I would say, to make sure that your model is behaving correctly. So that it's not only providing the result that you expect, but is using the feature that you expect. Because if at the end of the decision it's the one that you expect, but it's based on gender, it's very likely in the future that as soon as maybe the model, the data are going to change because of, I don't know, whatever behavior of people that are going to change. And in general, even if the model is working perfectly, you can be challenged because you can be sued because you are making decision based on gender, even if the final decision is maybe what you were expecting. So all those metadata are very important when you move out of, let's say, a laboratory exploration phase where you just play around with data and you say, okay, now I wanted to use them for reality.
Okay, thanks very much.
Welcome. Any other questions? I don't see you. Okay. Yeah, this is light. Sorry, but I cannot see you, so I was just going to.
Can you see me?
Yeah.
Thanks for the presentation. Awesome work. So whenever we talk about the interpretability and the explainability of AI models, this question always comes to my mind, that what is the cost that we are paying for this interpretability? And my suspicion is that we are paying in terms of robustness of our AI models. So if you, let's say, go to your slide number 35 or something, where you were doing some sampling to estimate, to get so to get an idea about the decision boundary, right? So there are some sampling-based attacks that employ exactly same technique to find the gradient of the decision boundary, and they use that to generate your adversarial samples, which is, in my opinion, a very high cost to pay if I just want to explain my outputs.
That's true. In general, I will say, I think that many of the current situation, but in general, even for the future, I expect that you will need to find your trade-off. And this is very domain specific. And at the same time, for example, explainability probably doesn't need to apply to literally every decision, because maybe, you just wanted to sample your scenario to understand if the model is still behaving as expected. Because yes, they are very costly in general, and you usually don't really need to, let's say, run them continuously. So the first step, of course, is try to choose a model that works for your scenario, but that has already have, I would say, a good enough level of interpretability out of the box. Because if I just get the result, I'm able as a human to explain. I'm able to understand the involved logic and use the additional techniques when essentially you need to do something more advanced.
I see. So is it right to say that I don't want to interpret each and every output, but just to get like a general idea of how the model is working?
Yeah. For the global explanation, usually, of course, it's an aggregator that tries to give you a general definition. Usually, sorry, I suggest to use the global explanation techniques before putting the model in production, because give you a general understanding about how the model overall is behaving. While for local explanation, it's more about auditing. That could be like an internal audit for compliance. So it's usually not something that you wanted to do for literally every explanation that, or every decision that you made.
Okay, makes sense. Thanks.
Any other? Okay, another question.
One more question.
So can you briefly explain how do you extract explanations from a neural network? I mean, that's basically a lot of hidden information in there. And how do you do that, if it is possible?
A neural network usually, that's, I will say, the hardest type of model to explain, because even if you provide the internal weight that the different layers of the algorithm has learned, for a human being, it's like, okay, it's 5 point whatever, so I don't really understand it. So there are different techniques and there are different, let's say, research topics about that. One of them aim to try to understand which subpart of the neural network is making a specific decision, so that you are able to understand. It's very similar to how a human brain works. So you're trying to realize what is the area of your brain that is making like the decision, or is more involved when you speak, or it's more involved when you, I don't know, dream and similar. So they are trying to understand if it's possible to extract this information from the neural network as a post-hoc analysis, so that you start from a neural network, you try to understand more or less which subnet is taking a decision, so that at least you can do this and say, okay, if I realize, this is more, let's say, I don't know if this was very clear from. Well, okay, it's not a good slide. So if you realize that a specific area of the neural network is the one that is recognizing, I don't know, the shape of the hair of this animal, you can try to understand if the model, at least, it's, I mean, again, as a human brain. So analyzing the behavior, I can try to understand if the area that I was expecting to be used has been used for the decision. But again, I will say it's if you are using a neural network, let's put it this way, probably you don't need, probably explainability is not your main requirement, because otherwise it's very hard that you can obtain proper visibility. But the way, of course, it's a field that we are investigating, and of course many other universities are investigating on it to try to how to mix and try to have a better explanation also for that.
So, thank you. You gave a very good practical overview, I would say, about the explainability, but is there any theoretical work being done about the feasibility of the whole thing? Because it seems like a trade-off between the abstraction or automatization of the model versus the human explainability. And
yeah, it's true. In general, even in the original presentation from DARPA about a sort of end goal for explainable AI in general, it's not realistic to aim to have a full explanation or the same level of explanation for all the type of models. So yes, that means that based on the critical aspect, the criticality of your decision, for example, if you're improving your internal process to, I don't know, you have a factory that builds specific object, and you have a quality gate that wanted to assure that the result it's respecting the guidelines. At the moment, usually you do a manual sampling, like it takes one product in the whole, let's say, for the whole day, and say, okay, let's test it manually and see if represent the expected limits. You can try to have a much deeper analysis using ML in that case, not to replace the human one, but to have a much deeper or a much wider coverage. So you have you still preserve your quality, let's say, assessment that is done manually, but you also have an algorithm that tries to mimic that one, and of course you can apply it to all the possible input, so to literally all the products, because you don't need to manually test it. So in a similar scenario, the explainability, it's less a concern, or I mean, it's mainly in the worst case scenario, you are discharging more product than you're supposed to be, and in that case, of course, it's mainly an internal risk. In that case, the reason of explainability is more about to minimize, of course, wasting of your money. But you have, I would say, a less constrained scenario, because I mean, you are already respecting the limit, the baseline limit that, I don't know, each country is asking, like you need to sample manually every, I don't know, 100, 1,000 different product. So you are just improving your quality, so you have probably a better product in the market, and you take the risk, of course, if you realize that the model has a false positive ratio of, I don't know, 1 every 2,000, you can say, okay, yeah, I accept that risk. So again, it's very domain specific. All these analyses, all those primitives, of course, are general purpose, but how to apply, it's very depending by your case. And also, you needed to really pay attention about which model you wanted to apply.
So time is up. Then thank you very much.
Okay. Feel free, of course, to reach me if you need any other question. If you have any other question. Thank you.